Okay, so the first thing that we're going to do in the separation of variables algorithm, step one, is we're going to assume that we can find solutions that have this very special form, u of xt is equal to h of t times phi of x. In other words, we can write the solution as a product of a function of t alone and a function of x alone. Now, at this point, there's no reason to believe that we should be able to do this, but we will see why we can do this. And most solutions are not going to be able to be written in this form here. What's going to happen is we're going to find infinitely many solutions of this form, and the solution to this problem will be a sum. The solution to the problem that we care about will be a sum of these product solutions. So the solution is a sum of these. Okay, so really we should be subscripting these with a k, but I'm not going to do that right now. Okay, so let's get at it. So what we're going to do now is we're going to assume that we can write the solution as h of t times phi of x, and we're going to say, well, if we can do that, what happens if we plug it in to the PDE? So we're going to plug it into the PDE. When I plug it into the PDE on the left-hand side, I'm just going to get h prime of t times phi of x. And on the right-hand side, where I plug it in, I'm just going to get h of t times phi double prime of x. And I see that's somehow my camera has gotten a little off whack here. So the tripod was not working, so now I just have it on a pile of books here. Big pile of books. And it doesn't always work well because the cable is pulling it. But you probably don't care about that. I once watched a Tom Scott video, and he said it's good to do stuff like this. It makes it seem realistic. Like I'm not just a math robot or something. All right, so this is h prime of t, and this is phi double prime. Okay, so let me get my notes so I can make sure I'm lining things up right. Okay, so now what we're going to do is we're going to rearrange this equation. When we rearrange this equation, we're going to get h prime over h of t. And on the right-hand side, we're going to get phi double prime of x over phi of x. Okay, so now notice what we have here. On the left-hand side, this is a function of t. On the right-hand side, this is a function of x. And we're saying that for all values of t and x, or at least x between 0 and pi and t greater than 0, for all of these values, these two functions are equal to each other. So what does that mean? Well, imagine if I vary t over here. If I vary t over here, x does not change over here. X and t are independent. So if I vary t, x doesn't change, and so the right-hand side doesn't change. So it means if I vary t over here, this function is not going to change, which means this function on the left-hand side is equal to some constant. Well, if the function on the left-hand side is equal to a constant, then the function on the right-hand side is also equal to a constant. And we're going to call this constant minus lambda. This is called the separation constant, though I will never use that term past now. Separation constant. The word that I prefer is eigenvalue. The word that I prefer is eigenvalue, and the minus sign, why is this a minus sign? This will become clear. This will become clear in a moment. Okay, why are we using a minus sign and just saying, instead of just saying equal to lambda? I mean, in principle it's the same, but the minus sign is going to be a convenience. So let me just illustrate for a moment why I call this an eigenvalue. And we're going to see more about why it should be called an eigenvalue in the upcoming videos on this problem. There's going to be a few of them. So I can, if I just look at my phi equation, what I get is phi double prime of x is equal to minus lambda phi of x. If I move the lambda, if I move the minus sign over here, okay, so what this is saying, if I consider the operator L phi is equal to minus phi double prime, I can write this equation as L phi is equal to lambda phi. And if I just think about L as being a matrix and phi as being a vector, this is the eigenvalue-eigenvector equation. So it makes sense to call lambda an eigenvalue. Why do I want to deal with the minus phi double prime instead of just phi double prime? I don't know if I'll mention this explicitly. I don't know if I'll remember to mention it explicitly when I do computations in a moment. But the reason is because it's a positive operator. Because what we're going to show, actually I can just say it right now. Lambda is going to be a positive number, so minus phi double prime, that operator is a positive operator, meaning its eigenvalues are positive. Okay. All right, so now I've got two ODEs. I have an ODE for H, I have an ODE for phi. And now step 2 is going to basically be to solve the equation for phi. So step 2 over here, solve. So this is like the answer to question 2 in the notes. So solve the phi equation. And here's where we're going to use the boundary conditions. Okay, so what do I know about phi and h here? Well, I know that u of 0t is equal to h of t phi of 0, and that's equal to 0. Okay, so what can I conclude here? Well, the product is equal to 0. So if h of t is equal to 0 for all t, if h of t is equal to 0 for all t, then u is trivial. In other words, u is identically equal to 0. Because u is equal to h of t times phi of x. If h of t is 0 for all values of t, then this means u is going to be identically 0. That is a solution to this equation aside from the boundary or the initial conditions here. It's at least a solution to this part here. But we're going to throw that solution out. One, because it's not going to work well. It's just going to be, we're going to be adding these, like I said, we're going to have an infinite number of these solutions. We're going to add them all up. Adding the 0 function doesn't make any sense. It also doesn't satisfy the initial condition here, but that's not the main reason. Okay, so it means that h of t is not 0 for at least some 0, or for at least some t. So if h of t is not 0 for at least some t, this is going to imply that phi of 0 is equal to 0. Just divide this by h of t and you get phi of 0 is equal to 0. I mean, you don't have to think about it this way. If you have two numbers whose product is equal to 0, one of them has to be 0. If h of t is not equal to 0, it means phi of 0 is equal to 0. And similarly, this will also imply if you replace the 0 with a pi, same computation or same idea implies phi of pi is equal to 0. Okay, so now we have quite a different type of equation that we're going to be dealing with. It's an ordinary differential equation, but it's an ordinary differential equation called a boundary value problem. So if I look at just my phi equation, what do I have? I've got phi double prime is equal to minus lambda phi, and I've got these boundary conditions that say phi of 0 is equal to phi of pi, and they're both equal to 0. So this is a boundary value problem. It is a much different problem than an initial value problem. So if you remember an initial value problem from your ordinary differential equations class, you were given maybe phi of 0 and phi prime of 0, and then you wanted to solve this equation. So initial value problems always have a unique solution. Boundary value problems do not always have a solution, and when they have a solution, it's not going to be unique. So this does not have a solution. This does not have a solution. this does not have a solution for all, this does not have a solution for all values of lambda. So this does not have a solution for all values of lambda. There's only some values of lambda for which it has a solution, and in fact there's not a lot. There are only a few values of lambda that are a solution, and when it does have a solution, it's not unique. When it does have a solution, it's not unique. Okay, so what I'm going to do next, I'm going to solve this boundary value problem. Solving the boundary value problem means actually finding the functions phi that satisfy this equation and also finding the lambdas that satisfy this equation. Or finding the lambdas that satisfy this equation and the phis that go along, for every lambda we're going to get different solutions. So that's what I mean by solving this boundary value problem. So again, I just need to check my notes to make sure I'm on the right thing here. Looks like it, yes. So actually, I got this step wrong a little bit. So step 2 is bring in the boundary conditions. Bring in the boundary values. In other words, find the boundary value problem, which is what we did here. Okay, so step 3 is going to have a few parts. The first part of step 3, I'll call it part A of step 3, is going to be solving the phi equation. So solve the boundary value problem. Notice for h, we're going to have h double prime is equal to minus lambda h, but we're going to figure out what lambda is first before we solve this equation. Okay, now I'm going to, as I was saying, I'm going to solve this boundary value problem under the assumption that lambda is greater than 0. So I'm assuming, let me write this in purple, let me write it in red to alert you to the fact that I'm assuming lambda is greater than 0. Well, why do I want to do that? Number one, because it's the truth, and I'll explain that in the next video. But number two, I have a second order differential equation, and the form of the solution, whether or not it's exponentials or trigonometric functions or some combination, is going to be determined by whatever lambda is here, whether or not lambda is real and whether or not lambda is greater than 0. So when I say assuming lambda is greater than 0, I mean it is a real number that is greater than 0. That's what I'm saying here. Okay, and so I'll prove that in the next video, but I'm going to solve this boundary value problem assuming that lambda is greater than 0, and that'll be it for this problem, for this video, I mean. So if I solve this, the general solution, if lambda is positive, minus lambda is negative. And so the general solution is going to be, this is from ODEs, if you don't remember this computation, we're doing the characteristic polynomial, just look it up. We've got phi of x is equal to a cosine square root of lambda x plus b sine square root of lambda x. Okay, so now I'm going to use my boundary values. If I plug in 0, I'm going to have 0 is equal to phi of 0. What do I have on the right-hand side? Well, if I plug in 0 to the sine, I get 0, so that term is 0 when x is equal to 0. Over here, if I plug in x equals 0, that's 1, so I'm just left with a. Okay, so a is equal to 0, so that term goes away. Now I'm going to plug in the boundary condition for pi, and here's where things for this problem get interesting. I've got 0 is equal to phi of pi, and what I'm going to have on the right-hand side now is b sine square root of lambda pi. And just to be clear, it's like that. Okay, so if b is equal to 0, I know a is equal to 0. If b is equal to 0, then phi of x is going to be equal to 0, and our solution is going to be identically equal to 0. So we know b is not equal to 0. So the only way this can be equal to 0 is if this sine is equal to 0. But the only way that can happen, pause for a minute and think about what this requires of lambda. The only way that can happen is if the square root of lambda times pi is equal to an integer multiple of pi. So in other words, we need square root of lambda to equal some integer. Some integer k for, right now, just k equals 1, 2, 3, 4, 5, because I'm assuming lambda is greater than 0. So what does this tell me? This tells me lambda is going to be equal to k squared, where k goes from 1, 2, 3, so on and so forth. In other words, for every positive integer, there's going to be another lambda, given by lambda is equal to k squared, for which there is a solution to this boundary value problem. And the solution to this boundary value problem is going to be b square root of lambda x. Square root of lambda is k, so it's going to be b sine x. So I'm going to erase all of this, so copy it down if you haven't. Okay, so the solution to this boundary value problem, I'm now going to call it phi k of x. I'm going to index it by k, the eigenvalue. Phi k of x is equal to bk, I'm going to call it bk sine of kx. Okay, so notice again, there's only solutions for when lambda k is equal to k squared, so I'll just record that here. Lambda k is equal to k squared because we're going to need it up here. So there's only solutions when when lambda is equal to the square of an integer. And notice that it's not unique. I can multiply this by any non-zero number and I'm still going to get a non-trivial solution. Okay, so let's now look. I have enough time. The equation for h is not going to be so hard. So for the h equation, so this is part b. I think that's part b, what I've labeled part b. Oh no, so start a, sorry, well, the handwritten notes that I will upload will be, I want them to be consistent, I guess. So solve the ODE. So that was just finding the solution, a cosine plus b sine. Part B is use the boundary values. So use boundary values. Use boundary values to find the lambda k's that are allowable. And then part C, this part is right. Part C, solve the h equation. So h equation. Okay, so the h equation is simple. We just have h prime equals to minus, well, what is lambda? Lambda is k squared minus k squared h. And the solution to this, the general solution, is going to be h of t is equal to some constant that I'm going to call c times e to the minus k squared t. Okay, and I'm going to just index this by k again. And notice I'm going to be multiplying these two solutions together. So I'm just going to, instead of having the c there, that constant will just be absorbed into this constant bk there. Okay, so that's where I'm going to stop in this video. The next video, when we come back in the next video, this part will be erased, and I'm going to show why lambda is real and why it's greater than 0. So stay tuned for that in the next video.